Okay, continuing with colligative properties. Now I'm going to show you the reverse, kind of like I did when we did solution concentrations. Instead of saying, okay, so many grams added to this volume and you get this molarity, what if I want to find the molarity? Well, you can do the same thing with colligative properties in freezing point. Okay, if I have 200 grams of water and instead of freezing at 0, like it normally freezes, I want it to freeze at negative 6.5. And I know I'm adding C2H5O. Okay, this is ethanol. Okay, so I'm going to add this to it, and I want to know how much do I need to add in order for it to freeze now at 6.5 instead of 0. Okay, well, if you remember the formula for freezing point, you take the molality times the constant. Okay, well, if I know the change in temperature and I know the constant, if I divide those two, I'll get the molality. So again, that's just simple formula manipulation. So you take the change in temperature divided by the constant and you'll get the molality. In this case, it's 3.49. It's nice. And again, remember, if it's lowering, it's negative. That's why those two cancel out. So remember, molality is kilograms times mole, or molality is kilograms and moles. Well, I have molality, 3.49. I have kilograms, 200 grams, 0.2 kilograms. That'll give me moles. So again, I just multiply the molality I have, the kilograms I have, and this is how many moles of ethanol that I find. All right, again, I don't have a mole meter, so I need to change this to grams because that I can weigh out. So take 6.98 moles of C2H5. Its formula mass, what it weighs, is 45 grams. So multiply them and I get 31.41 grams. This I can measure out. So if I go and I put 31.41 grams of ethanol on the scale, I measure it out, I add it to my 200 grams of water, I mix it up, and now instead of freezing at 0, like water normally does, it has to be negative 6.5 for it to freeze. Which, if you think about this winter, that probably won't happen. It hasn't been very cold, has it? Okay, so that's how you do the reverse. Okay, now we haven't talked about what they call the Van 't Hoff factor. See, we've just been doing molecular compounds. When you add a molecular compound, there's only one particle per unit, okay, one molecule. When we do ionic ones, though, they break down into ions. So actually, ionic compounds are better to add. That's why they use salt a lot, and the fact that it's cheap. But they break down into more particles, and remember, colligative properties are based on the number of particles. So the Van 't Hoff is the number of particles a substance becomes when it dissolves. It's the number of ions, okay? So when we did the slides before, those were molecular compounds. You don't have to worry about, that's that I in the formula. You don't have to worry about it because they only have one. They only have one particle per unit. But when you have an ionic compound, you have at least two. You can have many. You have to look at the formula and then that'll tell you how many particles. So honestly, if you want to change boiling point and freezing point, vapor pressure and all that, it's better to use an ionic compound. Okay? So for instance, NaCl has two. There's two ions. K2O has three. CaSO4. Now, SO4 is a polyatomic ion. It's just one unit, you guys. So that's two. Okay? So you do how many, if it was like Na3PO4, that would be four. Excuse me. Ooh. Okay? So you have to multiply that in there. Okay. What is the freezing point depression of a 0.8 molar solution of BaCl2? Okay. So we already have the molality. We don't have to find that. And how many ions do we have? Sorry. One and two more. So it has three. So now what we're going to have to do is we're going to have to take our molality times our constant, and then we're going to have to multiply by 3. Because this, when it breaks down, when you dissolve it, it makes 3 particles. And again, remember, that's what colligative properties are. It's the number of particles, not really what you add. So again, an ionic compound affects your colligative properties much more because you get way more particles. A molecular compound, you just get one, so you don't even have to figure it in the equation. Okay? The Van 't Hoff equation is 3 because barium chloride, 1 barium, 2 chlorine, breaks down into those ions. Okay, so now it's going to affect it. Now, if this was a molecular compound, it would be a third as much. Okay, so the ones I did before on all the slides before, those were all molecular compounds. They only affected one particle, per unit. Here we got to look at when you break down an ionic compound, how many ions you have. So again, the Van 't Hoff, they call it, I'm assuming he's the guy that figured out the particles. Um, it makes it much more, you change it much more when you have an ion compound. Okay. All right. Osmosis. Osmosis is the movement of water. And it's a semi-permeable membrane, you know, it allows things to go through. If you have any family that's on dialysis, you know, they use this process to get out there, you know, to clean their blood out when they do dialysis. But what happens is water moves to make sure that you get the same amount of stuff on both sides. Here there's more particles on this side than there is on this side. So what's going to happen is these particles are going to stay, but the water is going to move over here because it wants it to be the same concentration on both sides. So if you add more water over here, more particles, but they're going to be the same concentration. This is just going to have less water in it. So that's osmosis. Okay, osmotic pressure, you can actually add pressure on this side and keep those guys over there. So you can change, and again, it's the number of particles, it's a colligative property. You can change osmotic pressure by adding particles. Okay, the net movement of the solvent, again, which is usually water, from a solution to low to high concentration, that's osmosis. Osmosis is the movement of water. And again, the natural occurring thing is it wants to be the same on both sides. Okay, you can apply pressure to stop that. Okay, here's the formula. Pretty crazy. This is osmotic pressure. To me, it looks like pi. Sorry, but that's its formula. I, Van de Hoff. Number of moles, volume, R, T. R is a gas constant, T is temperature. Or if you can reduce it down, it's to Van de Hoff times molarity times R, and I'll give you R in a minute, times temperature. Okay, so I'll show you these. If two solutions are separated, by a semi-permeable membrane and have the same osmotic pressure, no osmosis will occur. They'll apply pressure to each other and they'll keep it equal. They won't allow it to happen. So here's what I'm talking about. Okay, osmotic pressure again is that pi thing. I don't know why it's that, you guys. I is the number of ions, like the Van de Hoff. M is molarity. Moles divided by liters. R is the gas constant. If you took 121 last semester, we talked about the gas constant. That never changes. Because again, we're working with pressure, we're working with gases, so the gas constant is 0.0821. And the temperature, because we're working in gases, has to be Kelvin. Okay? So basically, you fill in the numbers. Okay, find the osmotic pressure of a solution that has 43 grams of potassium chloride dissolved in 400 milliliters of water. The first thing I'm going to do is I'm going to find my molarity. So I'm going to change 43 grams of KCl into moles. Okay, 43 divided, just divide by its formula mass, 74.5. That's one potassium, one chlorine added together. So I take those two and I get 0.577 moles. Now define molarity, divide by 0.4, divide by liters. Okay, so now I found M. I got one thing done. Actually, I got almost all the rest of it done now. Okay, so I've got molarity. Osmotic pressure, I said, is I, which is the number of particles. Well, in KCl, that would be 2. M, I just found, 1.44. R is the gas constant, 0.0821. And the temperature has to be in Kelvin, so I take 273 plus 25. Okay, so I've got my number of particles is 2, 1 potassium, 1 chlorine. I found my molarity, which is 1.44. Gas constant, 0.0821. And then again, I changed this number to Kelvin by taking 25 plus 273. Okay, so I've got them all there. Just multiply and you get 70.46 atmospheres. Okay, that's the osmotic pressure it takes to keep this solution from moving, I guess you'd call it. That's the osmotic pressure it takes for this to happen. So again, 2 is the number of particles. 1.44, that's the molarity I found. I found moles and divided by liters, molarity. Here's the gas constant. That number is always the same. And then your temperature, if it's 25, I change it to 298 in Kelvin. Then just multiply. That's how you do osmotic pressure. Okay? Okay, so we have different types of solutions when we talk about osmosis. Isotonic is where nothing moves. They're the same on both sides. An isotonic solution, if you've ever had to have an IV, you get a saline solution. It's an isotonic because it's the same salt concentration, or it's the same as your solutions in your body. Okay, your salt solutions in your body. So when they give you IV, they give you IV fluids, they give you an isotonic solution, which is actually 0.9%. Okay, the membranes stay the same on both sides, they're not changing. Okay, hypotonic means there's a lower osmotic pressure and the solvent is going to leave the solution at a higher rate than it enters. Okay, hypo meaning it's lower osmotic pressure. Hyper is going to be higher. And I mean, they kind of go with it. Hypo means low, hyper means high. Okay, like hyperactive, you know, they're really high energy, whatever. Okay, so when these solutions occur, things can happen because of it. Okay, so if you have a hypotonic solution, you have a lower osmotic pressure and you're going to get solutions leaving at a higher rate than they enter. Here, they're going to be a higher rate than they came in. Here's just show you what happens with blood cells. Okay, here's our blood cells. So out here is your ice, you know, your normal body fluids, which I said is 0.9% salt solution. Okay, so they have a semi-permeable membrane. You know, our red blood cells are very important to us because they move oxygen around, they pick up waste and all that. So they move around and they have semi-permeable membranes so that they can pick up stuff. Now, if you take a red blood cell and you store it in a hypertonic solution, meaning high, they will shrivel up because what happens is, okay, out here you have higher, let's say, salt concentration out here. So what happens is the water inside the cell is going to say, hey, I gotta dilute that. So the water is going to leave, and then what's going to happen is your red blood cell is going to shrivel up. Okay, if you have low concentration out here, okay, what's going to happen is they're going to go in here and try to dilute this. Okay, if this has a higher salt concentration than out here, the water out here is going to say, oh, I got to make, because they want to be the same. Here's one where they're the same. The amount in and out are the same. They live, you know, in harmony, if you want to call it that. But when you've got low solute out here, which means there's a lot of water, then the water is going to go in there and it's going to try to make them the same. And what will happen is your red blood cell will, what they call lyse. Okay, it'll go kaboom, it'll blow. Here, what happened was because you had a higher concentration, let's say, we're just going to say salts, okay, out here. What's going to happen is the water is going to come out here and say, hey, I got to dilute this. It's got to be the same. And then the cell's going to shrivel up and they're going to call that crenation. Okay, so when it bursts, they call that hemolysis. All right, neither of them are good. You don't want either of them to happen. This is what you want. So that's why when you get, if you get dehydrated, this is going on. So they're going to give you fluids and they're going to make sure they're the same solution so this doesn't happen. Okay, and that's what happens with osmotic pressure. Okay, if you get an intravenous solution, you're going to get saline solution. There might be meds in there and stuff like that, but it's always going to be isotonic. It's going to be the same as your body solutions because you don't want either of these to happen. Okay. All right. I think we're going to quit there. The last part of this talks about other things besides solutions, and we'll do that in the next part. We're going to spend a little time going through some colligative properties, solving some of these problems. So that'll be what we'll do. And so we'll quit right here as far as the notes for this part.